Now, to consider what symmetry might do to help us analyze this problem, it helps really to look at this Hamiltonian and think about the symmetries that it has. Well, one symmetry jumps out at us immediately. The potential function itself, this harmonic potential, is in fact perfectly symmetric. So therefore we immediately know that we have parity symmetry, so that all of the solutions that we will find will have to be either even or odd functions of x. Very good. We could consider that symmetry, but there's a much deeper, much more important symmetry for this problem. And you can begin to see what it is when you look at the structure of the Hamiltonian. Apart from the values of various constants, what you notice is that the position and the momentum both appear as the square in this Hamiltonian. So it seems like there's something going on between position and momentum descriptions of this system. To understand really how to exploit this, it helps for us to review very quickly how we carried out the symmetry approach in the case of the parity operator, and then build up a parallel looking at the oscillator. Now, in terms of parity, we began by looking at considering a change in representation. We wanted to find a different way of looking at our problem, but where the problem had to be the same even under that different viewpoint. In this case, that change in the representation of the problem was simply to take the x-axis and to imagine we had arbitrarily chosen the x-axis to run in the precisely opposite direction. Right? The symmetry comes in later when you realize that even if you do flip the x-axis, the Hamiltonian had to have the same structure. So the first thing we want to do is think about a change in representation. Now, for the harmonic oscillator, we are interested in this asymmetry between the momentum representation and the position representation. Very good. So we want to think about them making a change, for example, from the momentum representation, changing between that, right, and the position representation. That is going to be the change that we are going to be considering. The next step in terms of defining the symmetry is we then had to define a corresponding operator that would carry us from one representation into the other representation. Well, certainly we know, I'm sorry, this doesn't have the tilde. That's just the position representation. We know how to do that, right? The way we carry between these two representations is we could start, for example, with the momentum representation, and then of our wave function, and then the operator we would apply would be the Fourier transform operator. So that will play the role of the parity operator. Next, what we are charged with doing is thinking about what the Hamiltonian looks like in the new representation. And we had gone through this argument that showed actually once you define the operator, the flipped Hamiltonian would have this property. Another way of looking at it is we're just computing what the Hamiltonian looks like in the flipped representation by multiplying both sides on the right by the inverse of the corresponding symmetry operator, a formula perhaps along these lines. Now, we could certainly carry out this formula using our Fourier transform, but in essence, we have already done that type of a thing because we know how to write down the Hamiltonian in either the position or the momentum representation. We have a very beautiful way of doing that, right? This is the position representation of the Hamiltonian. We also happen to know the momentum representation of the Hamiltonian. We get that by using the various operators. So in position representation, we know that the position operator is just x, and that the momentum operator is h bar on I times d by dx. In the momentum representation, we can get the Hamiltonian by using these replacements for our operators. The position operator in the momentum representation is actually I times d by dk. That's something you guys had proved earlier. And then the momentum operator in the momentum representation is simply multiplication by h bar times k. Now, there's one issue that we face, though, that we have to contend with, and that is if I write down then my Hamiltonian operator in this representation, in the in the momentum representation. I already have it written down in the position representation, but let's just do this for the record. So in position representation, the Hamiltonian then is going to be minus h bar squared on 2m times 2x derivatives plus 1/2 m omega squared times x squared. If I compute that in the momentum representation, right, the first term is p squared on 2m. P is h bar k, so I get h bar squared k squared divided by 2m, or h bar squared divided by 2m times k squared. That's the momentum part. Then that's the kinetic energy part. For the potential energy, we have 1/2 m omega squared times the square of x. But in the momentum representation, x has this value. When I square this, I will get a minus sign, and then I will have two derivatives with respect to k. So this is my Hamiltonian then in the two different representations. And I'd like you to notice that indeed these are almost identical. Here I have two derivatives with a minus sign in front, and here I have two derivatives with a minus sign in front. Here I have x squared with a plus sign in front, and here I have k squared with a plus sign in front. I'm just a little bit off. In other words, the prefactor on the x squared here is m omega squared, whereas over here it's h bar squared on m. It's different. And notice it kind of is different in the backwards way when I compare the prefactors in front of the derivatives. So if I could only find a way to manage these constants, to make them somehow magically go away, then I could get myself into a situation where the Hamiltonian is actually identical in both representations. And that then is how we finally came to our key conclusions when we had looked at parity. Because once the Hamiltonian, the final consequences of symmetry come when the Hamiltonian is identical in both representations. When that becomes the case, that tells you then that you can replace this flipped Hamiltonian with the original Hamiltonian. So then the Hamiltonian and your symmetry operator commute, and then all of these great consequences follow, that if you are looking at a bound state, the operator applied to the bound state should also be a bound state. In our case, that would mean the Fourier transform of our state should also be a bound state. And because we are in one dimension, just like we were with parity, because we are in one dimension, and there is only one solution per energy state, that would mean that not only is phi is also then a pure state with respect to our symmetry operator, either parity in the parity case, or in this case of the pure state of the Fourier transform operator. And we will think a bit in a moment what that would exactly mean. But before we can really say any of that, we have to deal with the fact that we have these different values for our constants when we write the Hamiltonian in the different spaces.